All right, so a little gram to gram stoichiometry problem, right? So anytime we have a stoichiometry problem, we've got an equation. So this is a nice single replacement reaction. Now this one I've written out and it looks okay, but really metal oxides, when we put them in water, turn into metal hydroxide. So this, even though I've written it okay, wouldn't really happen this way in real life. They would both turn into a manganese hydroxide and aluminum hydroxide, unless you did this not in water. We'll do one here in a few weeks called the thermite reaction, where you've got some oxides and stuff and they're not turning into, they're not dissolved in water. But typically we think of single replacement as happening in water. But let's pretend that the question you were given by your evil chemistry teacher is 7.23 grams of aluminum. And we want to know what's the theoretical yield of aluminum oxide. Right? We want to know what's the theoretical yield for aluminum oxide. A theoretical yield is how much we should make. So that's your just standard stoichiometry problem. We wouldn't call this a theoretical yield, right? Because that's what we're using to react it with. So if we calculated the grams of manganese oxide that we would need, we wouldn't call that a yield, right? We yield the things over here. So I could have two theoretical yields. I'd have to actually do the lab to do it. Let's pretend. I don't even have any idea what our numbers are going to be. I know it should, right? Ideal-wise, it should get heavier, right? Because we're adding oxygen to it. So I'm going to make up a number. Let's say we mix some chemicals, it blows up. This wouldn't blow up. And that's going to give us, let's call it 12 grams. So if we do this lab and we get 12 grams of aluminum oxide, right? Let's say we filtered it and it ended up on the filter paper. We subtract the mass of the filter paper. We get 12 grams. So I already know my actual yield, but I don't know my theoretical yield. On the test, you're not going to get up and do a lab, but I'm going to tell you what an actual yield is. All right, that's too much talking. So my steps are, I'm going to go from grams to moles of my aluminum, then a mole bridge, moles of aluminum to moles of aluminum oxide, and then a molar mass, moles of aluminum back to grams of aluminum oxide. Because this equation, when I balance it, is a mole balance equation, not a mass balance equation, right? So when I see this, I've got 3 here and only 1 here, so I'll put a 3 here. That gives me 3 manganeses. And I've got 2 aluminums, so I'm going to put a 2 here. So I know, that's one of the reasons I kind of like to write it out on paper and see it like this. I know I'm going to have a 2-to-1 mole bridge. I've just got to get those outside molar mass steps, right? So I can do that middle mole bridge step. So we'll start with let's use different colors here so we can see our different steps. So we've got our 7.23 grams of aluminum. Oh, my shoulder's sore. I got my vaccine last night, so my shoulder's a little sore. So I've got grams of aluminum. The way to go between grams and moles is off of our periodic chart. So if I look up aluminum, 26.98, I don't multiply it by 2. I take care of subscripts here. I take care of coefficients in my mole bridge. So I just do 26.98 grams of aluminum for every 1 mole of aluminum. Now, since I balanced it in black, I'll flip to black. And you should be pausing and working ahead of me on this. This is not chem appreciation. This is definitely, you should be able to do chemistry. Figure out which one goes on top and bottom. Since I've got moles of aluminum, I'll do the 2 moles of aluminum down here. That came from right here. And I will do my 1 mole of aluminum oxide on top. And then I'll do our last step. They ask us what our theoretical yield was. We're wanting it in grams, which is kind of normal, right? If they only asked for it in moles, I would have been done here. If they said how many moles of aluminum oxide, I'm done right now, right? Because it has moles of aluminum oxide right here. But we don't measure in moles, we measure in grams. So if they want a theoretical yield, it's probably going to be in terms of grams. So I need the molar mass of aluminum oxide. To get that molar mass of aluminum oxide, I'm going to do the molar mass of aluminum times 2 and the molar mass of oxygen times 3, right? So 26.98 for aluminum times 2 plus 16.00 times 3. Mathematically, those 2 zeros don't matter, but scientifically they do. I know because I wrote that 3, that 3 is a good value, right? It's somewhere between 2 and 4 because it's the last one I wrote. If you round things off, right, 16 versus 16.00, this is somewhere between, in science, right? This is, if it's a measured value, 16 is somewhere between 15 and 17. 16.00 is somewhere between 15.99 and 16.01. So this is a much more precise value, right? So we add those together, 2 aluminums and 3 oxygens, keeping our digits. since I've got 1 mole of aluminum oxide here, or since I've got moles here, I'll do moles of aluminum oxide here, and 101.96 grams of aluminum oxide here. So now, for my theoretical yield, I would multiply by the top and divide by the bottom. So 7.23 times 101.96 divide by 26.98 divide by 2. I'm dividing by both of these. You can hit divide by multiply, but you got to put parentheses if you do that kind of thing, right? Some people like to multiply everything on the top and get a number. Multiply everything on the bottom and get a number, and then do the top divided by the bottom. That's fine. However you like to do your math, do that right now, and you should get 13.7 grams of aluminum oxide. That's my theoretical yield, right? 13.7 grams of aluminum oxide is my theoretical yield. So that's what I would answer. So when Mr. Fred guessed 12 grams as an actual yield, remember I said we did it and we actually got 12 grams. So if I wanted my percent yield, and that's on that, there's a reminder on the back of your periodic chart, that kind of thing we should do like in our chemical workshop. We take the actual divided by the theoretical times 100. I was using the basketball analogy the other day for a lot of students when we were talking about it. If you take 50 shots and you make 40 of them, right? Your theoretical yield was 50. Your actual yield was 40. Your percent, you do 40 divided by 50 times 100, so 80%, right? So when they talk about the percent that somebody shoots, it's the same kind of thing, right? So we'll take our actual, which is 12 grams. I'm going to have to give you that on the test, right? Or you physically did it in the lab, divided by my 13.7 grams times 100, right? Because it's a percent, so we times it by 100. So 12 divided by our answer from before, and that gives us 87.8%. Notice I was recording 3 digits here. I had 3 digits here. I kept more than that on these. And these are based on each other, so we can ignore them. So my answer should have 3 significant figures, 3 measured figures, basically, right? So at 87%, 88, almost 88% is our yield on this. You should definitely have that in your chemical workshop, and you should definitely be able to do that for our 9-week.